When we look at the night sky, what we see is really an illusion. Stars, galaxies, and glowing nebulae fill our eyes with light, and we instinctively assume the universe must be full. But if we could step far enough back to see the entire cosmos at once, we would realize something shocking. All that light is just a thin layer scattered across a vast, silent darkness. The truth is simple and unsettling. The universe is far emptier than we imagine. And these enormous empty regions are not passive or irrelevant. They quietly influence the expansion of the universe, the motion of galaxies, the way light travels, and even how old we believe the universe is. Today, we explore the hidden architect of the cosmos, cosmic voids, the immense dark regions that shape everything we see. This is not a story about stars. It's a story about where stars are not. A cosmic void sounds like a place with absolutely nothing inside, but the reality is more complex. A void is a region where the matter density is 20 to 30% lower than the cosmic average, spanning hundreds of millions, even billions, of light years. Inside a typical void you'll find extremely few atoms, almost no gas, very weak dark matter density, and only isolated dwarf galaxies. This difference may seem small, but stretched across astronomical distances, it becomes a cosmic force. So how did these vast voids form? After the Big Bang, the early universe was not perfectly uniform. Some regions were slightly denser than others. Over billions of years, dense regions grew denser. Underdense regions became even emptier, and the underdense pockets gradually expanded into the colossal voids we observe today. Some voids are 300 million light-years wide. Some reach over 1 billion. A single void could easily engulf thousands of galaxies, yet contain almost nothing. These dark regions aren't gaps in the universe. They're part of its foundation. On large scales, galaxies are not scattered randomly. They form a structure that looks like a vast spiderweb. This structure is called the cosmic web. It has 3 main components: filaments, long, thread-like structures where galaxies flow like rivers; nodes, dense intersections where massive galaxy clusters form; voids, the enormous empty cavities between the filaments. Here's the surprising part. The shape of the universe is determined not by where galaxies are, but by where they aren't. As voids expand, they push the surrounding filaments outward, compressing them and guiding matter into clusters. In other words, voids grow, filaments tighten, galaxies arrange themselves along these squeezed lines. If you could view the universe from above, you wouldn't see a map of glowing stars. You'd see a map shaped by darkness. Now we reach the most astonishing part. The Milky Way sits inside one of these enormous voids. It's called the KBC void, named after the astronomers Keenan, Barger, and Cowie. Its estimated diameter, 1 to 2 billion light-years. This means we are observing the universe from inside a massive cosmic depression. And this changes everything. 1. We may be mismeasuring galaxy velocities. Light travels differently in an underdense region. Less matter, less gravitational pull, less distortion. This can make nearby galaxies appear faster or slower than they really are. 2. It might explain the Hubble tension crisis. Astronomers get 2 different expansion rates for the universe. One from nearby galaxies, one from the early universe. Why don't they match? A leading theory is, we are measuring the universe from inside a giant void, so our local expansion looks faster than average. 3. It could shift our estimate of the universe's age. If the expansion rate appears faster here, our age calculations could be off. In short, we are not observing the universe from a flat landscape, but from inside a cosmic pit. This pit bends the window we're looking through. Light travels at a constant speed, but its journey and its appearance change depending on the environment. In cosmic voids, light loses less energy, experiences weaker gravity, bends less, and arrives looking slightly younger. This affects our measurements. Redshift is distorted. Because the void expands faster than dense regions, galaxies can appear to be receding more quickly. This alone can make the universe seem like it's expanding faster than it really is. Time passes differently. According to general relativity, time runs slower in dense regions, faster in empty regions. Voids are empty enough that this time flow difference becomes significant over billions of years. Supernova brightness is affected type Ia supernovae. The standard candles of cosmology can appear brighter or dimmer depending on the void's structure. This contributes to errors in distance and age calculations. In short, voids act as invisible lenses, reshaping the universe we think we see. The influence of cosmic voids doesn't stop with the present. They shape the future of the universe as well. 1. They compress filaments. As voids expand, they push the cosmic web into sharper, thinner structures. 2. They mimic cosmic acceleration. The rapid expansion of voids may imitate part of the dark energy effect. Some models suggest that 20 to 30% of dark energy might actually be void dynamics. 3. They determine where galaxies form. Galaxies are born on the edges of voids, not inside them. Voids decide the cosmic geography. 4. The universe is becoming emptier. As billions of years pass, filaments thin out, galaxies drift apart, and voids grow even larger. In the far future, the universe will be a vast darkness, punctuated by a few lonely islands of stars. The universe's future is not bright. It is empty. Cosmic voids are not just empty spaces. They behave almost like pockets of accelerated expansion. Inside a void, the internal pressure is lower, gravity is weaker, and space stretches slightly faster than average. This led scientists to a bold question. Could part of what we call dark energy actually be the effect of cosmic voids? Some modern cosmology models suggest that, as voids grow, they push the surrounding filaments outward. This outward push creates an additional expansion effect, something that looks like dark energy from our point of view. If much of our observational data comes from inside or near voids, we might be overestimating the speed of cosmic acceleration. This doesn't mean dark energy doesn't exist, but it does mean cosmic voids might be contributing to the acceleration we observe. It's one of the most debated ideas in cosmology today, and it reshapes how we think about the universe's long-term fate. In the far future of the universe, it won't be galaxies that dominate the landscape. It will be voids. If you could jump trillions of years ahead, voids would be vastly larger. Filaments would thin and eventually break. Galaxy clusters would drift apart. The bright cosmic web would slowly fade. The universe would become, on the largest scales, almost completely empty. As voids grow, matter becomes more sparse, energy flows weaken, galaxies drift away until they can no longer see one another. Eventually, the universe becomes a place of silent cosmic loneliness. The structures we study today, filaments, clusters, webs, networks, will be gone. In that distant era, one force will have shaped the cosmos more than any other: the slow, relentless expansion of cosmic voids. Cosmic voids don't just shape the structure of the universe, they shape how the universe evolves over time. In dense regions, galaxies interact, merge, collide, and form new stars through gravitational compression. But inside and around voids, the rules are very different. Voids stretch matter apart, reducing interactions, weakening galaxy formation, and slowing the internal activity of the cosmic web. As voids expand, they thin out the cosmic filaments, reduce star formation across entire regions, isolate galaxy clusters from one another, and gradually weaken the universe's ability to build complex structures. It's a slow but unstoppable process. Imagine a cosmic ocean where currents are fading, leaving islands of galaxies drifting alone. Voids act like engines of cosmic dispersal, quietly eroding the universe's interconnectedness. In this sense, voids are not just empty spaces, they are active participants in cosmic evolution. They are the silent forces that slowly unweave the fabric of the universe. When we think about the universe, we imagine stars, galaxies, nebulae, and clusters. the bright things. But the more we study the cosmos, the more we realize a profound truth. The universe is defined by what is missing, not only by what is there. Void regions dominate the cosmos by volume. They outsize galaxies, clusters, and filaments by orders of magnitude. If the universe were a landscape, the bright parts would be tiny mountaintops, while voids would be the endless valleys between them. This shift in perspective changes everything. It reframes how we understand cosmic evolution. It reshapes how we measure distances, time, and expansion. It challenges our interpretation of dark energy. It forces us to rethink our cosmic address. We are not living in a universe made of shining structures. We are living in a universe held together by vast oceans of nothingness. And yet, this nothing is powerful. It shapes the flow of matter. It guides the evolution of galaxies. It bends the path of light. It defines the future of the cosmos. In the end, voids are not empty at all. They are the silent architects of the universe we think we see. For centuries, humanity searched for answers in the brightest parts of the sky. But today we know. The true architects of the cosmos are not the glowing stars, but the silent voids between them. Cosmic voids shape the expansion rate, guide the motion of galaxies, alter the passage of time, distort light, mimic dark energy, and write the universe's long-term fate. And the most astonishing truth, we live inside one of these enormous voids. We are observing the universe through a warped window carved by emptiness. And that leads us to a new understanding. If you want to understand the universe, you must first understand the places where nothing exists. Because in the cosmos, emptiness is not an absence, it is a force. This journey is only beginning. In the next episode, we explore the mysterious acceleration of the universe and what dark energy might truly be. The universe is quieter than we imagined, and far more powerful.